Hi guys, today I wanted to explain how to design a code decoder for the 7-segment display. The 7-segment display is this guy here, okay? So it is a display with several 7-segment display, like disposed here. How does it work? The 7-segment display, I mean. Each segment has a letter, like A, B, C, D, E, F, G, and you can use these to represent numbers or and letters. For instance, for the code 1, B and C must be 1. Let me use the red, so it is more realistic. For the code 2, A, B, G, E, and D should be equal to 1. For the code 3, A, B, G, A, B, G, C, and D, and so on. So how we can design something that can do this? So for a 4-bit input, we have to design a lookup table which takes as an input x0, x1, x2, and x3, and as an output can guarantee us that these 7 segments are on. So it must have 7 outputs like this: 2, 4, 6, 7, and each output corresponds to the segment of the 7-segment display: A, B, C, D, E, F, G. How we can do this in VHDL? In VHDL, you don't need always to write y assigned to A and B like this. You are not obliged to use always logic gates. You can also use another technique which allows the VHDL to synthesize the function with multiplexer. What I mean is that maybe in some cases like this, you know this is not a question mark, because in this case you know the logic function. So you know the function f of x. You know this function here, the logic function. But you don't know the combination of the logic gates that produce this function here. You can either have two ways at this point. You can either use Carnot map, so you can either do the long process, so write x1, x0, x1, x2, x3, the outputs A, B, C, D, and etc. Then take all the ones here. I'm explaining it very quickly, and perform a very big Carnot map, in which here you plant the value of x and A, B, C, D, E, F, G, 0, 0, 0, 1, 1, 0, 1, 1, and basically you report the ones here. I'm just doing very fast, like 1, 1, 1, 1, and you perform some circle. I will explain the Carnot map method in another video. But in this case, it is very big, and but it is optimized. What we want to do now is to take the other route, in which we know the function f of x, but we don't know the logic gates to synthesize the function. And so we will write the function f of x in this case, and we will let VHDL synthesize as many as multiplexer as it wants to perform the function needed. The multiplexer, the single multiplexer, can be used to synthesize as many functions as you want. So in this case, we will perform this route here. Okay, we will write that the output A, B, C, D, E, F, G is equal, for instance, to 1 when x is equal to 0. Naturally, it is a vector, so this is 1, 1, 1, 1, etc. When x equal to 0, 0, 0, 0, etc. This is the way that you, in the case that you know the function, but you don't know, or the process to assimilate the function will be too big, and you rely on the autosynthesis function of the VHDL through multiplexer. And so we will proceed in doing this way instead. So let's open Quartus. And let's open new project wizard. Let's select in the desktop, let's select VHDL projects, and let's call this as segment display. This is very important because we will use this guy in other projects. So segment display, we will select this folder here, and the entity of this project will be segment display. Next, 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 finish. Okay, sometimes the Quartus does this error here. Do not panic. Just open Quartus with as an administrator, and it should be fine. Let's go on desktop and VHDL projects, segment display, and open this guy here. So now let's use the new, and let's use the VHDL file. As always, let's open an already made project so that we have so that we can skip all the like this multiplexer here, so that we can actually skip the entity, the boredom of writing the syntax all over again. So we will use the entity here. Let's empty that what we don't need. Okay, thanks. Entity segment display. We have to write this guy here. Okay, so we have 4 inputs and 7 outputs. So x will be input standard logic vector 3 down to 0. And the output will be A, B, C, D, E, F, G. Output standard logic vector 6 down to 0. And now we will write that A, B, C, D, E, F, G is equal to, so let's start from 0. So from 0 we need to color basically everything except for G. You can do that with this A, B, C, D, E, F. This is 0. So, and 8 is the same what with the one at last. So 1, 1, 1, 1, 1, 1, 1, 2, 4, 7, 2, 4, 6, 7, and the 0 here. When the input x is equal to 0, 0, 0. To write this, we have to we have 2 methods. You can write when 0, 0, 0, 0 like this, and right here with x select, which is probably the easiest way. So this is 0. As a comment, this is 0. And now let's write the others. We can immediately write also 8, just because it is the same what with the one here. For the one we just need BC, so we can copy this guy basically 8 times. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And of course, we needed to also write the statement. I forgot the comma. And 0000 when others. Okay, so this is 1. For the 1, we needed to also just B and C. So this is A, B, and C. So the other are 0. For the 2, we need A, B, G, E, and D. So everything 1 except for F and C. So number 2 is 1, 1, 0, 1, 1, 0, 1. Number 3 is 1, 1, 1, 1, 0, 0, 1. Number 4 is this guy here. So we need B and C, G and F. So number 4 will be 0, 1, 1, 0, 0, 1, 1. Number 5, I need a blank one. Five is like this. So the first is A, 0, 1, 1, 0, 1, 1. So we need 1, 0, 1, 1, 0, 1, 1. And for the number 6, you can watch this number here and imagine a number if you can, but it is 1, 0, 1, 1, 1, 1, 1. 7 is the easiest because it has the first 3 are connected. So 1, 1, 1, and the other all 0. 8 is the easiest, sorry, because it is all 1. And 9, it is all 1 except a 0 here. So it is like this. E is equal to 0. So this is 0. Okay. So I think that there will be. Let's go into this. Save it. Let's run the simulation. There will probably be some mistakes in the syntax, of course. Okay. I forgot to write segment display. Okay. Let's run the simulation. Yes. Okay, can't determine the type of object near a string X. Uh, No, it was right before. Um, no, it is correct. A, B, C, D, E, F, G, A, B, C, D, E, F, G. When 0, 0, 0, 3 down to 0. Okay, let's use the other method. Ah, okay, you don't need to... Ah, okay, sorry. You don't need to write A, B, C, D, E, F, G all over again. Sorry. I copied and pasted so many times that I actually forgot that you don't need to write the output all over again each time. Sorry, my bad. So it is like this. Sorry about that. I really didn't notice. So let's run the simulation. Now it should work. 0, 0, 0 over... Ah, okay. Oops. I also forgot to write the choice. So 0, 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 0, 4, 0, 0, 5, 0, 0, 6, 0, 0, 7, 0, 0, 8, and 0, 0, 9. Okay, he's right. Okay, so now it works. Now, before running the simulation, let's check if actually he synthesizes a lot of multiplexer like we expected. So let's go on tools, netlist viewers, and RTL viewer. As you can see, he synthesized the function with a lot of multiplexer, like we expected. So now let's run the simulation, and let's use file, new, University Program UF, insert, node finder, list, everything to the right, okay, and let's zoom a bit, and let's try with some blank, and let's see if it does work. Now let's try. First, let's ungroup this guy here. Sorry, let's ungroup. No, sorry. My bad. There was no need to. Okay, let's ungroup the input, and let's write, for instance, 8. So this guy is equal to 1, and the other to 0. Then we will write 9. No, let's write this number here, and then this, and then number 9, and then also this number here. So let's run the simulation. Run function simulation. Yes. Save. Okay, so let's zoom. The first number is 1000. 1000 is, according to my simulation, here I wrote 8. So when I have 1000, 11111 should be the output. And In the first case, I have 1, 1, 1, 1, 1, which is of course 8, as you can see. Now I have this number here, which is 1, 1, 0. 1, 1, 0. Let's see. The combination here is everything to 1 except for B. Let's discover the number. Six. Yes, that's right. It's 6. Let's go on. This is 1001. 1001 should be 9. I have everything to 1 except A, B, C, D, E. So let's go. A, B, C, D, skip, F, G. 9. Let's do the last. This is 1, 1. Ah, okay, I could use this. 1, 1. And as an output, I have 1, 1, 1, 0, 0, 1. Let's color everything. 1, 1, 1, 1. 1, 1, 1, 1. 0, 0. 0, 0, and 1. 3. Yes. So, it is working properly, in my opinion. And we will use this guy here in also as a block for other projects. In the next video, I will show you how to use the Carnot map, and in the other video, after that, I will show you how to perform a binary to digital converter. So you put, for instance, 1, 0, 1, 1 as a binary, and you have in the 7-segment display, you have 1, 2, for instance. In this case, is 3. I think that we can end this video now, and thank you guys for your attention, and see you in the next video.